Hello and welcome everyone. I'm Iftikhar Ahmed and welcome to the talk on using relative lines of code to guide automated test generation for Python. Many testing tools offer rapid on-the-fly automatic testing of software using random testing. For the software under test, a property-based testing tool allows a user to specify some correctness properties and usually includes some default properties, such as that executions do not throw uncaught exceptions, and generates random input values for which the properties are checked. Developers seem to expect such tools to conduct their testing within at most a minute in order to provide rapid feedback on newly introduced faults during development, when the fault is easiest to identify and fix. The claim that a minute is a typical expectation is derived from the 1 minute timeout for the very widely adopted Python hypothesis tool. Even tools for generating Java unit tests such as EvoSuite and Randoop also have default timeouts of 1 minute. Testing with a limited budget is critical for using property-based testing in a continuous integration setting, where testing time per task on a large project is limited. However, it is unlikely that low probability faults will be exposed in 60 seconds using pure random testing. Coverage may help, but it is too expensive. So that's why small budgeted automated test generation techniques needs methods that improve on pure random testing, but require no additional computational effort. And relative lines of code can help with this. Before talking about relative lines of code, let's talk about lines of code. Lines of code, or LOC, is a simple way to measure the size or complexity. It may mean number of carriage returns or number of statements. However, it is not a reliable measure as it depends on many things, including programming language. The same program may require different amount of lines of code depending upon the programming language. So we cannot compare LOC across different languages. Also, LOC depends on the developers and many other things. Though LOC is not a reliable measure, relative LOC, on the other hand, provides useful information. For example, between two functions f and g, if you know that f has more lines of code than g, you may prefer testing f to testing g. And why is that? Because prior research shows that larger functions are usually more error-prone. Zhang et al. Showed that 20% of the largest modules contain 51 to 63% of the defects. Ostrand et al. Showed that the largest 20% of files contain between 59 to 83% of the faults. Some prior work has investigated into this area. For example, Vazar prioritizes code regions with deep and interesting paths. Randoop and other feedback-based approaches obtain part of their effectiveness from an indirect avoidance of short function. To the best of our knowledge, the size of functions has never been used as a factor in the decision of which API calls to be tested in automated test generation. We hypothesize that the longer a function on average takes more complex data types as arguments or returns more complex data types as results than shorter ones. Our research goal is to investigate the effectiveness of this hypothesis for test generation. More formally, in this study, we tried to answer the following three research questions. How does LOC heuristic compare to random testing in terms of fault detection and code coverage? How does LOC heuristic compare to coverage-guided testing, such as genetic algorithm and swarm testing? And our third research question was, how does combined generation approaches, such as genetic algorithm combined with LOC heuristic, compare to using only one test generation heuristic? Due to shortage of time, I will not go into the details of the methodology that was applied for this study. I will give a high-level overview of the steps that were used for the empirical analysis. So we start by selecting 14 Python libraries, and then we performed unguided random testing, swarm testing, genetic algorithm for test generation, and calculated coverage information and fault detection rate. We also calculated LOC and used that to generate test cases using only LOC, and also using LOC in swarm testing, genetic algorithm, and then calculated the coverage information and fault detection rate and compared with unguided random testing. We ran each test generation method 100 times for 60 seconds on each SUT and used those runs as a basis for evaluation. Now, looking at the results, graph on the left side show the result for RQ1 in terms of the faults detected. As you can see from the highlighted boxes, LOC-based approach identified more faults compared to random test generation, specifically for 11 of the 15 SUTs. The table on the right side shows the comparison in terms of coverage, both branch and statement coverage. The mean gain in branches covered for LOC compared to pure random testing was 219 branches with a median gain of 146 branches. In the second research question, we compared coverage guided testing such as genetic algorithm and swarm testing with LOC heuristic. As you can see from the highlighted boxes, in terms of identifying faults, LOC heuristic is statistically significantly better than all other methods where a mean of 4.07 faults per run is detected. In terms of coverage between LOC and swarm had the best coverage, 85.2 for both statement and branch coverage. In terms of genetic algorithm, LOC was better for branch and statement coverage, 80.2% for branch coverage and 80.4% for statement coverage. In the third research question, we combined generation approaches such as genetic algorithm with LOC heuristic and compared with using only one test generation heuristic. Swarm testing had the worst fault detection results by a large margin with a mean of only 5.8% of maximum failures. Swarm with LOC improved on this, but only to 10.6%. The next best method, the genetic algorithm with LOC, only detected a mean of 3.6 faults per run. In terms of coverage, swarm with LOC performed slightly better than LOC alone in terms of coverage, 83.2% branch and 83.4% statement coverage. The genetic algorithm using the LOC heuristic was the most effective method, and combining the genetic algorithm with LOC produced mean branch coverage of 84.2% and mean statement coverage of 84.5%. Next, we also wanted to compare with feedback-directed random testing. So we performed a preliminary experiment using the Randoop Java implementation. We used Randoop and biased the probability in favor of larger methods in exactly the same way as with Python testing. We used a set of 1177 Java classes taken from 27 projects hosted on GitHub. The results are at high level, similar to those of Python. The LOC heuristic is sometimes less effective, but more often produces an improvement in test effectiveness. And using the LOC heuristic increased mean branch coverage by 17.3% and statement coverage by 13.9%. So based on these results, the obvious question then becomes, is relative line of code the silver bullet? No, that's not the case. As we can see that in our data set, LOC heuristic performed worse than random testing in 4 cases and in terms of branch coverage, and in 1 case in terms of fault detection. However, this is true for almost all techniques. In practice, few test generation heuristics are close to universally being effective, and even though they are useful, the heuristic may prove ineffective in some cases, as we saw that in coverage-driven genetic algorithm and swarm testing, both perform worse than pure random testing in terms of branch coverage for 5 systems under test, and worse in terms of fault detection for 3 and 2 systems under tests respectively. This obviously doesn't mean these are bad methods, merely that they are heuristics. The next question might be, why is LOC heuristic so effective when it works? One possibility is during a 60-second test run, not all classes are explored by pure random testing. The LOC heuristic ensures that the classes that are never chosen are usually ones with a small LOC count. If you can't cover everything, at least cover the big methods. Our results indicated that the relative LOC of software components can provide valuable information for using in automated test generation, which opens up the opportunity to investigate the LOC heuristic further. One promising next step is to modify the heuristic to also bias testing towards executing code that has been the subject of a static analysis tool's warning. Also, we can use more sophisticated measures such as coupling metrics or complexity metrics in place of simple LOC. Thank you for watching the talk. I would be happy to answer any questions you have.
Hi everyone, welcome again. This is the Q&A session for the paper titled Using Relative Lines of Code to Guide Automated Test Generation for Python. This is a paper published in TOSEM, so it's a first journal paper. And we have here Iftekhar Ahmed, ready to answer any questions you might have. So please start posting your questions in the chat. While the questions start to show up, I would just like to get an idea of how you come up with this intuition that perhaps we should look into relative lines of code instead of very complex metrics as people tend to do. It feels like a little bit of a counterintuitive idea, and it would be nice to see how the idea was conceived.
So thank you, Jose. That's a very nice question. So our intuition was derived from the from the observation that when we're doing all the other analyses, right? So we were seeing these functions or methods in different programming languages that they tend to be more complex. They tend to deal with more complex data structures or data in general. So that led us to thinking, if I have only a limited amount of time to test, let's say 60 seconds, which is like one of the most default numbers or amount of time for many of the test generation tools, the default one. So we thought most likely it should help us to find it should give us more coverage, and hopefully it will help us finding more bugs in those complex, longer methods or functions that are dealing with more complex data or data structures. So that's essentially where this heuristic originated from. And also there was a prior work by Alex Dross, one of the co-authors of this paper, on swarm testing. So they also saw that, like whenever you are trying to, again, not directly related, but the intuition developed over time, over a period of time. So they looked at swarm testing and they saw that when you're splitting, right, when you're trying to do a bunch of, you're trying to in parallel, trying to test a bunch of configurations, you get more fault identification or you get more out of the testing. So, bringing all of these things together essentially led to this basic idea of, let's see what happens if I test the parts that are bigger, and given the amount of time is limited, let's see if we get a gain. So just to add to on top of that, as you saw in the result, or if you saw in the presentation, that it's not guaranteed that you will always gain a lot, right? It's not a silver bullet. You will, in some cases, you will see more gain in terms of coverage, in terms of fault identification. In some cases, it just falls flat. So, and that's true for many techniques, right? It's not, most of the techniques are not the silver bullet. It does not outperform all other technique in all possible scenarios. So yeah, that I think is what led to the thinking. I hope that answers your question.
Yeah, pretty much, yes. Very nice. I have another question related to the methodology. It came as a surprise a little bit that pure random was used as a baseline. Would you be able to say a bit more about how the approach could compare against more advanced techniques?
So we did not only compare with pure random, right? So we compared with genetic algorithm and also swarm. And as the result shows, I mean, obviously it does better than pure random. And the intuition is, again, goes back to the basic idea that we have limited amount of time, 60 seconds per se. So within that amount of time, if I'm randomly testing, the likelihood of, reaching some important thing or reaching more of the code may not be feasible, may not be possible in all possible cases. So in the paper, we mentioned this, like if I have a limited amount of time, I should spend more on the part that I think are more important, right? And since this part is big, this portion of code is relatively bigger, it should get more of our budget. So coming back to your question, comparing with other techniques, advanced techniques such as GA or genetic algorithm or swarm testing, our technique outperformed in many cases for many of the SUTs, but not for all of them, similar to what I was saying earlier. And also to add to that, we compared with AFL and also we compared with random in Java, right? Similar results that it does better in some cases, it doesn't better doesn't do as good in some cases, but the high level idea still persists that if you have two functions, f and g, and one of them is relatively bigger than the other, you get more bang for your buck if you start testing with a bigger one, relatively bigger one.
It makes sense instead of just using one metric or one goal. Would it make sense to have a combination of goals instead? Is that something that you have played with, perhaps?
That's actually a very nice question, and we haven't played with that, but that's in our future work, because as you're saying, right, so trying with different combinations of easy to calculate metrics, right? So the intuition or the basic idea was we don't want to calculate coverage within 60 seconds. We don't have the time. So let's calculate LOC, which is very, very cheap in terms of time and resource. So if there are other metrics, and we know there are so many other metrics that are easy and cheap to understand, and trying their combination and seeing how they actually, like, do they outperform, or how do they perform in comparison with even the simplest approach that we use, not pure relative LOC based approach. The intuition is, yes, it should outperform LOC or our approach that we propose in this paper, because so for example, if you have a function which is relatively higher in lines of code, plus let's say it's more complex, right? We did not measure we did not use any measurement of complexity per se. Our intuition was the complexity is embedded in it. Let's say we add the measurement of complexity. Let's say we add a measurement of understandability. We know that the measurement of understandability is yet to be, we don't have a pure good metric for measuring that, but let's say we have that. Adding those conceptually or intuitively should lead to better results given the short period of time. But I mean, we haven't played with that, but that is one of our future goals.
Thank you very much. I don't see more questions in the chat, so perhaps we have still 2 minutes in the session, and we could either wrap up or just give you an opportunity to talk a little bit more, and I try to do the latter. Could you elaborate a little bit more on the future directions for this work? What are you looking into as a result of these results that you have now?
So as we were saying, we are thinking of looking into other metrics, right? And what would be other cheap metrics that we can take? So that itself is a big, like a lot of exploration is to be done in that area. So that's one obvious feature direction. The other thing that we did is we compared with only 14 Python libraries, right? So increasing that number to greater than 14, maybe 50, 100 something, and to see if we get more confidence regarding our results. So in other words, what I'm trying to say is, in our result currently we saw that for 14 libraries, in some cases we do good, some cases we don't do so good. But if we increase the numbers, do we see a different trend? Maybe for a larger data set, our technique outperforms in majority of the case. So that would be in our favor. But that is a secondary thread of research. The primary thread is essentially looking more into additional metrics, or more fancier metrics, you can say. Let's say cyclomatic complexity. If we take that, add that, and do we get better coverage? Do we get better fault identification? So that's essentially the future direction that we're looking into at this point.
Sounds like a very promising direction. There is another question by Salil. He's asking about whether you could combine this with another technique. We don't have time, I'm afraid, to take on this question now, because the Q&A session will end. But Salil, please follow Iftekhar to the discussion room for this paper at the end of this Q&A in like 30 seconds. And I'm pretty sure that he will be happy to discuss this with you. Sure. Iftekhar, thank you very much for the very nice paper, very nice work, and for the presentation and for answering the questions here. And to all the audience, thank you very much for attending the session, and I hope you enjoy the rest of the conference. Thank you very much.
Thank you, Jose. Thank you for the nice questions. Thank you, everyone, for watching the video.